According to the 2020 National Electrical Code, specifically Table 310.16, when using 90 degrees C THHN copper conductors, a number 12 American wire gauge (AUG) wire has an ampacity of 30 amps. The derating factor for having 3 or more current-carrying conductors in a raceway, or conduit, is 70%. To determine the allowable ampacity, you multiply the base ampacity of the wire by the derating factor. In this case, that would be 30 amps multiplied by 70%, which equals 21 amps. Since the overcurrent protection is 20 amps, and that is less than the calculated allowable ampacity of 21 amps, the use of number 12 THHN copper conductors in a 3/4-inch electrical non-metallic tubing and conduit is acceptable. The inspector's rejection seems to stem from a misunderstanding of how to apply derating factors in conjunction with the ampacity ratings provided in Table 310.16. It is important to clarify a few key points regarding conductor ampacity, temperature ratings, and derating to fully understand why your interpretation of the code is correct. Firstly, let's discuss conductor ampacity and temperature ratings. The ampacity of a conductor is the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Table 310.16 of the National Electrical Code provides ampacity ratings for various conductors based on their insulation type and temperature rating. Conductors are typically rated for 60 degrees C, 75 degrees C, and 90 degrees C. It is crucial to select conductors with an appropriate temperature rating for the application, considering both the ambient temperature and the termination temperature ratings of the connected equipment. Secondly, let's clarify temperature correction and derating. Temperature correction and derating are necessary when conductors are used in conditions that differ from those assumed in Table 310.16. These adjustments account for higher ambient temperatures or the presence of multiple current-carrying conductors in a raceway or cable. The goal is to ensure that the conductor's insulation temperature does not exceed its rated value, which could lead to premature aging or failure. For ambient temperature correction, if the ambient temperature exceeds 30 degrees C, which is 86 degrees F, you must apply a correction factor to the conductor's ampacity. These correction factors are provided in tables accompanying Table 310.16 and are based on the conductor's insulation temperature rating. For conductor derating, when more than 3 current-carrying conductors are installed in a raceway, cable, or directly buried in the earth, the ampacity of each conductor must be derated as specified in Table 310.15. This derating is necessary because the heat generated by multiple conductors can raise the overall temperature within the raceway or cable, potentially exceeding the insulation temperature rating. Thirdly, let's explain the application to your situation. In your scenario, you are using number 12 THHN copper conductors, which have a 90 degrees C insulation rating. According to Table 310.16, these conductors have an ampacity of 30 amps when operating at 90 degrees C. You have 9 current-carrying conductors in a 3/4-inch ENT conduit. Since there are more than 3 current-carrying conductors, you must apply a derating factor. For 4 to 6 conductors, the derating factor is 80%. For 7 to 9 conductors, the derating factor is 70%. Therefore, you use the 70% derating factor. After applying the 70% derating factor, the allowable ampacity of the number 12 THHN conductors is 30 amps multiplied by 70%, which equals 21 amps. The circuit breakers protecting these conductors are rated at 20 amps. Since the overcurrent protection of 20 amps is less than the allowable ampacity of 21 amps, your installation is compliant with the NEC. The inspector's concern might stem from mistakenly believing that the 20 amp breaker size should be used as the starting point for ampacity derating. However, the NEC clearly states that the ampacity is determined by Table 310.16 and then adjusted for ambient temperature and the number of conductors. The overcurrent protection is based on the adjusted ampacity but cannot exceed the conductor's rating. It is important to note that the 20 amp overcurrent protection is the maximum allowed for number 12 copper conductors per NEC 240.4. The use of number 12 THHN conductors is permissible if the calculated ampacity after derating is greater than the breaker size. In summary, you are correct in your interpretation of the code. The number 12 THHN copper conductors with the 90 degrees C insulation rating have an initial ampacity of 30 amps per table 310.16. With 9 current carrying conductors in a raceway, the derating factor is 70%, resulting in an allowable ampacity of 21 amps. Since the conductors are protected by 20 amp circuit breakers, the installation meets NEC requirements. It is advisable to discuss your interpretation with the inspector, providing the relevant code references, specifically Table 310.16 and the derating factors from Table 310.15. This should help clarify any misunderstandings and ensure compliance with the electrical code. Remember to always consult the latest edition of the NEC and any local amendments to ensure accurate and up-to-date information. Understanding these principles is essential for safer and compliant electrical installations. Let's elaborate further on several aspects to provide a more comprehensive understanding. We can start with a detailed look at the specific sections of the National Electrical Code, NEC, that govern conductor ampacity, derating, and overcurrent protection. This will provide a solid foundation for understanding the rules and how they apply to your situation. Then we can review the NEC Table 310.16 in detail. This table provides the allowable ampacities for insulated conductors rated up to and including 2000 volts, 60 degrees C through 90 degrees C. It is important to understand how to read and interpret this table correctly. We will identify the columns for conductor size, insulation type, and temperature rating and demonstrate how to find the appropriate ampacity for a given conductor. Next, let's look at NEC Table 310.15. This table provides adjustment factors for ambient temperature and the number of current carrying conductors in a raceway or cable. We will focus on the adjustment factors for the number of conductors, as this is the primary issue in your case. We will also show how to apply these adjustment factors to the ampacity found in Table 310.16. After that, let's clarify NEC Section 240.4, Protection of Conductors. This section outlines the rules for overcurrent protection of conductors. It states that conductors must be protected against overcurrent in accordance with their ampacities. However, there are exceptions to this rule, such as the next higher standard overcurrent device rating rule, which allows you to use the next highest standard overcurrent device rating under certain conditions. Then we will talk about NEC Section 310.15, Ampacity Adjustment Factors. This section covers the requirements for adjusting conductor ampacities based on various factors, including ambient temperature, number of conductors in a raceway or cable, and the presence of other heat-producing equipment. We will focus on the adjustment factors for the number of conductors, which is the main concern in your case. Next, we will cover about calculating the derated ampacity. We will walk through the steps of calculating the derated ampacity for your specific situation, using the appropriate tables and adjustment factors from the NEC. This will provide a clear and concise example of how to apply the rules correctly. After that, we will discuss about the importance of proper documentation. We will emphasize the importance of documenting all calculations and code references to support your installation. This will be helpful when discussing your installation with the inspector and can prevent future misunderstandings. Let's also discuss some common mistakes to avoid. We will highlight some common mistakes that electricians make when applying derating factors and overcurrent protection rules. This will help you avoid these mistakes and ensure that your installation is compliant with the NEC. Next, let's explain the difference between ampacity and overcurrent protection. We will clarify the difference between ampacity, which is the maximum current a conductor can carry continuously, and overcurrent protection, which is the device that protects a conductor from excessive current. We will explain how these two concepts are related but distinct. After that, we will discuss about the role of the electrical inspector. We will explain the role of the electrical inspector and how they ensure that electrical installations comply with the NEC. We will also provide tips for communicating effectively with inspectors and resolving any disagreements. Let's also briefly touch on the different types of conductors. There are various types of conductors available, each with its own insulation type, temperature rating, and ampacity. We will briefly discuss some of the most common types of conductors, such as THHN, THWN, and XHHW, and their respective properties. And lastly, we will discuss the importance of safety. Electrical work can be dangerous, and it is essential to follow all safety precautions when working with electricity. We will emphasize the importance of wearing appropriate personal protective equipment, such as safety glasses and gloves, and following lockout/tagout procedures when working on de-energized circuits. By covering these additional aspects, you will have a more thorough understanding of conductor ampacity, derating, and overcurrent protection, and you will be better equipped to handle any electrical installation situation. We will also cover some related topics that can help you deepen your understanding of electrical installations. We can start with voltage drop calculation. Voltage drop is the decrease in voltage along a conductor due to its resistance. It is important to calculate voltage drop to ensure that the voltage at the end of the circuit is sufficient for the connected equipment to operate properly. We will discuss the factors that affect voltage drop, such as conductor length, conductor size, and current, and we will show you how to calculate voltage drop using the appropriate formulas. After that, let's briefly talk about grounding and bonding. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to trip the overcurrent device and prevent electrical shock. Bonding connects all metal parts of the electrical system together, which helps to equalize the voltage and prevent electrical shock. We will discuss the different types of grounding and bonding systems and the requirements for each. Then let's discuss about conduit fill calculations. Conduit fill is the percentage of the cross-sectional area of a conduit that is occupied by conductors. The NEC limits the amount of conduit fill to prevent overheating and damage to the conductors. We will discuss the rules for conduit fill and show you how to calculate conduit fill using the appropriate tables and formulas. And then let's briefly cover about short-circuit current calculations. A short circuit is an abnormal condition in an electrical circuit where current flows through an unintended path with very low impedance. Short circuit currents can be very high and can cause significant damage to electrical equipment. It is important to calculate short circuit currents to ensure that the overcurrent devices are properly sized to protect the equipment. Lastly, let's talk about harmonics. Harmonics are distortions of the sinusoidal waveform of alternating current. Harmonics can be caused by nonlinear loads such as electronic devices and fluorescent lighting. Harmonics can cause overheating of electrical equipment, increased energy losses, and interference with other electronic devices. We will briefly discuss the sources and effects of harmonics and some of the methods for mitigating them. Let's explore the NEC articles related to the subjects that we just mentioned. We will start with NEC Article 210, Branch Circuits. This article covers the requirements for branch circuits, including the number of outlets allowed on a circuit, the types of loads that can be connected to a circuit, and the overcurrent protection requirements. After that, we will discuss about NEC Article 215, Feeders. This article covers the requirements for feeders, which are the conductors that supply power from the service equipment to the branch circuits. We will discuss the requirements for feeder ampacity, overcurrent protection, and voltage drop. Then let's talk about NEC Article 220, Load Calculations. This article covers the requirements for calculating the electrical load of a building or structure. We will discuss the different methods for calculating the load, including the standard method and the optional method. After that, we will mention NEC Article 230, Services. This article covers the requirements for services, which are the conductors that bring power from the utility company to the building or structure. We will discuss the requirements for service ampacity, overcurrent protection, and grounding. And then let's talk about NEC Article 250, Grounding and Bonding. This article covers the requirements for grounding and bonding of electrical systems. We will discuss the different types of grounding and bonding systems and the requirements for each. Lastly, let's discuss about NEC Article 300, wiring methods. This article covers the general requirements for wiring methods, including the types of raceways and cables that are allowed, the installation requirements for these wiring methods, and the requirements for supporting and securing the wiring. Here are some additional details about the factors that influence conductor ampacity. These factors are ambient temperature. The ambient temperature is the temperature of the air or other medium surrounding the conductor. High ambient temperatures reduce the ability of the conductor to dissipate heat, which decreases its ampacity. The NEC provides correction factors for adjusting conductor ampacity based on ambient temperature. Next is conductor insulation. The type of insulation used on a conductor affects its ampacity. Different insulation materials have different temperature ratings which determine the maximum temperature that the conductor can withstand without damage. Conductors with higher temperature ratings can carry more current. Then there is conductor size. The size of the conductor affects its ampacity. Larger conductors have lower resistance, which means they generate less heat when carrying current. Therefore, larger conductors can carry more current than smaller conductors. After that is number of conductors in a raceway or cable. When multiple current-carrying conductors are installed in a raceway or cable, the heat generated by each conductor can raise the overall temperature within the raceway or cable. This reduces the ampacity of each conductor. The NEC provides derating factors for adjusting conductor ampacity based on the number of conductors in a raceway or cable. Then there is frequency of current. The frequency of the current flowing through a conductor affects its ampacity. Higher frequencies cause more heat to be generated in the conductor due to skin effect. Therefore, conductors carrying high frequency current have lower ampacities. There is also voltage drop. Excessive voltage drop can cause equipment to malfunction or fail. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. When calculating conductor size, it is important to consider voltage drop in addition to ampacity. Lastly, there is type of load. The type of load connected to a conductor affects its ampacity. Continuous loads, which are loads that operate for 3 hours or more, require conductors to be sized at 125% of the load current. Non-continuous loads, which are loads that operate for less than 3 hours, can be sized at 100% of the load current. We will now discuss the materials that are used to construct conduits. First, there's rigid metal conduit, RMC. RMC is a heavy-duty steel conduit that is suitable for use in a variety of applications, including underground, exposed, and concealed locations. RMC provides excellent physical protection for conductors. Then there's intermediate metal conduit, IMC. IMC is a lighter weight steel conduit that is similar to RMC but is easier to bend and cut. IMC is suitable for use in many of the same applications as RMC. After that there's electrical metallic tubing, EMT. EMT is a thin-walled steel conduit that is commonly used for indoor wiring. EMT is easy to bend and cut and is relatively inexpensive. And then there is flexible metal conduit, FMC. FMC is a flexible steel conduit that is used to connect electrical boxes and equipment. FMC is useful for applications where movement or vibration is expected. Next is liquid-type flexible metal conduit, LFMC. LFMC is a flexible metal conduit that is covered with a liquid-type plastic jacket. LFMC is suitable for use in wet locations. After that there is rigid polyvinyl chloride conduit, PVC. PVC conduit is a non-metallic conduit that is lightweight and corrosion resistant. PVC conduit is suitable for use in underground and wet locations. And lastly, there is electrical non-metallic tubing, ENT. ENT is a flexible non-metallic conduit that is commonly used for indoor wiring. ENT is lightweight and easy to install. Let's discuss the use of different types of conductors in various applications. We'll start with THHN or THWN conductors. THHN thermoplastic high heat resistant nylon coated, and THWN thermoplastic heat and water resistant nylon coated conductors are general purpose building wire that are commonly used for residential, commercial, and industrial wiring. THHN is suitable for dry locations, while THWN is suitable for wet or dry locations. Then we have XHHW conductors. XHHW, cross-linked polyethylene high-heat resistant water-resistant conductors are commonly used for underground service entrance cables and for wiring in conduit. XHHW is suitable for wet or dry locations. After that there's use conductors. Use underground service entrance conductors are designed for direct burial in the earth. Use conductors are commonly used for underground service entrance cables. And then there are MC cable conductors. MC, metal-clad, cable consists of insulated conductors enclosed in a metal sheath. MC cable is commonly used for commercial and industrial wiring. Next is AC cable conductors. AC, armored cable is similar to MC cable but has a different type of metal sheath. AC cable is commonly used for residential wiring. After that there is NM cable conductors. NM, non-metallic, cable consists of insulated conductors enclosed in a non-metallic sheath. NM cable is commonly used for residential wiring in dry locations. And lastly, there is SC cable conductors. C, service entrance cable is used to connect the service equipment to the building or structure. SC cable is available in both above ground and underground versions. Let's talk about some common electrical tools and equipment. We will start with multimeters. Multimeters are used to measure voltage, current, and resistance. They are essential for troubleshooting electrical circuits. Then there's wire strippers. Wire strippers are used to remove the insulation from electrical wires. They are available in a variety of sizes to accommodate different wire gauges. After that there's pliers. Pliers are used to grip, cut, and bend wires. They are available in a variety of styles, including line-ends pliers, needle nose pliers, and diagonal cutting pliers. And then there are screwdrivers. Screwdrivers are used to tighten and loosen screws. They are available in a variety of sizes and styles, including flathead, Phillips, and Torx screwdrivers. Next is conduit benders. Conduit benders are used to bend conduit to the desired shape. They are available in both manual and hydraulic versions. After that there's fish tape. Fish tape is used to pull wires through conduit. It is a long, flexible tape that can be inserted into the conduit and used to pull the wires through. Then there's cable cutters. Cable cutters are used to cut electrical cables. They are available in a variety of sizes to accommodate different cable sizes. And then there are voltage testers. Voltage testers are used to check for the presence of voltage in an electrical circuit. They are an essential safety tool for electricians. Lastly, there are ground fault circuit interrupters, GFCIs. GFCIs are used to protect people from electrical shock. They detect ground faults and interrupt the circuit to prevent injury. In addition to the tools and equipment we just mentioned, there are many other specialized tools and equipment that electricians use. These tools and equipment are essential for performing electrical work safely and efficiently. We will now be covering several of the most common electrical components. Firstly, circuit breakers are protective devices that automatically interrupt the flow of electricity in a circuit when an overload or short circuit occurs. They are designed to protect electrical equipment and prevent fires. Secondly, fuses are similar to circuit breakers, but they use a fusible link that melts and breaks the circuit when an overload or short circuit occurs. Fuses are typically less expensive than circuit breakers, but they must be replaced after they blow. Thirdly, receptacles are electrical outlets that provide a convenient way to connect electrical devices to the power supply. They are available in a variety of types, including standard duplex receptacles, GFCI receptacles, and USB receptacles. Fourthly, switches are used to control the flow of electricity to electrical devices. They are available in a variety of types, including single-pole switches, double-pole switches, and three-way switches. Fifthly, light fixtures are devices that hold and support lamps, providing illumination for a space. They are available in a wide variety of styles and designs to suit different applications. Sixthly, electrical boxes are enclosures that protect electrical connections and provide a safe and convenient way to mount electrical devices. They are available in a variety of sizes and materials to suit different applications. Seventhly, conductors are wires or cables that carry electrical current from the power source to the electrical devices. They are available in a variety of sizes and installation types to suit different applications. Eighthly, transformers are electrical devices that transfer electrical energy from one circuit to another, typically with a change in voltage. They are used in a variety of applications, including power distribution, electronic equipment, and audio systems. Ninthly, motors are electrical devices that convert electrical energy into mechanical energy. They are used in a wide variety of applications, including appliances, power tools, and industrial machinery. And lastly, generators are electrical devices that convert mechanical energy into electrical energy. They are used to provide backup power during power outages and in remote locations where there is no access to the electrical grid. Let's talk about the color codes for electrical wiring. Understanding the color codes for electrical wiring is essential for safety and for ensuring that electrical circuits are properly installed and maintained. The color codes help electricians identify the different types of wires in a circuit, which reduces the risk of electrical shock and other hazards. We'll start with black wire. Black wire is typically used for the hot wire in a circuit. The hot wire carries the electrical current from the power source to the electrical device. Next, we'll talk about red wire. Red wire is also used for the hot wire in a circuit, but it is typically used for switch legs or for the second hot wire in a 220-volt circuit. After that, we'll mention blue wire. Blue wire is sometimes used for the hot wire in a circuit, but it is more commonly used for switch legs and lighting circuits. Then we'll mention white wire. White wire is used for the neutral wire in a circuit. The neutral wire carries the electrical current back from the electrical device to the power source. Next, we'll talk about green wire. Green wire is used for the grounding wire in a circuit. The grounding wire provides a path for electrical current to flow back to the power source in the event of a fault, which helps to protect people from electrical shock. And lastly, we'll mention bare copper wire. Bare copper wire is also used for the grounding wire in a circuit. It is typically used to connect the grounding electrode to the electrical panel. Let's also talk about National Electrical Manufacturers Association (NEMA) enclosure types. NEMA enclosure types are standards that define the environmental protection provided by electrical enclosures. These standards are developed by the National Electrical Manufacturers Association (NEMA) and are widely used in the electrical industry to specify the appropriate enclosure for a particular application. NEMA enclosure types are based on the degree of protection they provide against various environmental conditions such as dust, water, ice, and corrosion. The NEMA enclosure type is typically indicated on the enclosure's nameplate. We will now cover some of the most common NEMA enclosure types. Firstly, Type 1 enclosures are general-purpose enclosures that are designed to protect against contact with live electrical parts and against falling dirt. They are suitable for indoor use in relatively clean environments. Secondly, Type 2 enclosures are drip-proof enclosures that provide protection against dripping water. They are suitable for indoor use in locations where condensation or splashing water may occur. Thirdly, Type 3 enclosures are dust-tight and rain-tight enclosures that provide protection against dust, rain, and sleet. They are suitable for outdoor use in locations where these conditions are likely to occur. Fourthly, Type 3R enclosures are rain-proof and sleet-resistant enclosures that provide protection against rain and sleet. They are suitable for outdoor use in locations where these conditions are likely to occur. Fifthly, Type 4 enclosures are watertight and dust-tight enclosures that provide protection against water, dust, and ice. They are suitable for indoor or outdoor use in locations where these conditions are likely to occur. Sixthly, Type 4X enclosures are watertight, dust-tight, and corrosion-resistant enclosures that provide protection against water, dust, ice, and corrosive agents. They are suitable for indoor or outdoor use in locations where these conditions are likely to occur. Seventhly, Type 7 enclosures are hazardous location enclosures that are designed for use in Class I, Division 1 hazardous locations. These locations are areas where flammable gases or vapors are present in the air under normal operating conditions. Eighthly, Type 9 enclosures are hazardous location enclosures that are designed for use in Class Roman II, Division 1 hazardous locations. These locations are areas where combustible dust is present in the air under normal operating conditions. Ninthly, Type 12 enclosures are industrial use enclosures that are designed to provide protection against dust, dirt, oil, and non-corrosive coolants. They are suitable for indoor use in industrial environments. And lastly, Type 13 enclosures are oil-tight and dust-tight enclosures that provide protection against oil, dust, and non-corrosive coolants. They are suitable for indoor use in industrial environments where these conditions are likely to occur. It's important to note that the specific requirements for each NEMA enclosure type are defined in the NEMA standards publications. These publications provide detailed information on the construction, testing, and performance requirements for each enclosure type. The choice of NEMA enclosure type depends on the specific environmental conditions that the electrical equipment will be exposed to. It is important to select an enclosure that provides adequate protection against these conditions to ensure the safe and reliable operation of the equipment. Here are some additional considerations for selecting NEMA enclosures. Firstly, consider the ambient temperature. The ambient temperature is the temperature of the air surrounding the enclosure. The NEMA enclosure must be able to withstand the ambient temperature without overheating or degrading. Secondly, consider the humidity. The humidity is the amount of moisture in the air. The NEMA enclosure must be able to withstand the humidity without corroding or degrading. Thirdly, consider the chemical exposure. The chemical exposure is the presence of chemicals in the environment. The NEMA enclosure must be able to withstand the chemical exposure without corroding or degrading. Fourthly, consider the physical impact. The physical impact is the possibility of the enclosure being struck by objects. The NEMA enclosure must be able to withstand the physical impact without being damaged. Fifthly, consider the ingress protection IP rating. The ingress protection IP rating is a two-digit number that indicates the degree of protection provided by the enclosure against solid objects and liquids. The first digit indicates the protection against solid objects, such as dust and dirt. The second digit indicates the protection against liquids, such as water and oil. And lastly, consider the Underwriters Laboratories ALL listing. The Underwriters Laboratories ALL listing indicates that the NEMA enclosure has been tested and certified by Underwriters Laboratories to meet the applicable safety standards. Here are some common electrical formulas to keep in mind. We'll start with Ohm's law, which states that voltage equals current times resistance, or volts equals amps times ohms. This formula is used to calculate the relationship between voltage, current, and resistance in an electrical circuit. Next, we have the power formula, which states that power equals voltage times current, or watts equals volts times amps. This formula is used to calculate the power consumed by an electrical device. After that, we have the voltage drop formula, which states that voltage drop equals current times resistance times length, or volts equals amps times ohms times feet. This formula is used to calculate the voltage drop in an electrical circuit. Then we have the wire size formula, which is circular mils equals 2 times K times I times D divided by voltage drop, where K is the material constant, I is the current in amps, and D is the distance in feet. This formula is used to calculate the appropriate wire size for an electrical circuit. And lastly, we have the motor horsepower formula, which states that horsepower equals volts times amps times efficiency divided by 746. This formula is used to calculate the horsepower of an electrical motor. Let's talk about the different types of electrical drawings and diagrams. We will start with single-line diagrams. Single-line diagrams are simplified representations of an electrical system that use single lines to represent conductors and symbols to represent electrical components. They are commonly used to show the overall layout of an electrical system and the relationships between different components. Then we have schematic diagrams. Schematic diagrams are more detailed representations of an electrical circuit that show the connections between all of the components. They are commonly used for troubleshooting and repair work. After that, we'll mention wiring diagrams. Wiring diagrams are detailed representations of the physical wiring of an electrical system. They show the location of all of the wires, connectors, and other components. Then there are panel schedules. Panel schedules are tables that list all of the circuits in an electrical panel and the loads that are connected to each circuit. They are used to keep track of the electrical loads in a building and to ensure that the panel is not overloaded. Next, there are riser diagrams. Riser diagrams are vertical representations of the electrical system in a multi-story building. They show the location of all of the electrical panels, feeders, and branch circuits. After that, there are lighting plans. Lighting plans are drawings that show the location of all of the lighting fixtures in a building. They are used to plan the lighting for a space and to ensure that the lighting levels are adequate. And lastly, there are power plans. Power plans are drawings that show the location of all of the electrical outlets and equipment in a building. They are used to plan the power distribution for space and to ensure that there are enough outlets to meet the needs of the occupants. We'll now talk about electrical safety practices. Electricity can be dangerous, so it's important to follow safety precautions when working with electricity. Here are some electrical safety practices to follow. Firstly, always de-energize circuits before working on them. This is the most important safety precaution to follow. Before working on any electrical circuit, always de-energize it by turning off the circuit breaker or removing the fuse. Secondly, use the right tools and equipment. Always use the right tools and equipment for the job. Make sure that the tools and equipment are in good condition and that they are properly insulated. Thirdly, wear personal protective equipment (PPE). Wear personal protective equipment (PPE) such as safety glasses, gloves, and insulated shoes. This will help to protect you from electrical shock and other injuries. Fourthly, never work in wet conditions. Never work on electrical circuits in wet conditions. Water is a good conductor of electricity, so working in wet conditions can increase the risk of electrical shock. Fifthly, inspect electrical cords and plugs regularly. Inspect electrical cords and plugs regularly for damage. If you find any damage, replace the cord or plug immediately. Sixthly, never overload electrical circuits. Never overload electrical circuits. Overloading a circuit can cause the wires to overheat and start a fire. Seventhly, use ground fault circuit interrupters (GFCIs) in wet locations. Use ground fault circuit interrupters (GFCIs) in wet locations such as bathrooms, kitchens, and outdoor areas. GFCIs will protect you from electrical shock if there is a ground fault. Eighthly, test circuits before energizing them. Test circuits before energizing them to make sure that they are properly wired and that there are no shorts or ground faults. Ninthly, follow lockout/tagout procedures. Follow lockout/tagout procedures when working on electrical equipment. This will help to prevent someone from accidentally energizing the equipment while you are working on it. And lastly, know your limits. Know your limits and don't try to do electrical work that you are not qualified to do. If you are not sure how to do something, call a qualified electrician. Let's cover the different types of overcurrent protection devices. Overcurrent protection devices are used to protect electrical circuits from excessive current, which can cause overheating, damage to equipment, and fires. There are several different types of overcurrent protection devices, each with its own advantages and disadvantages. We'll start with circuit breakers, which are automatic switches that open a circuit when the current exceeds a certain level. Circuit breakers can be reset after they trip, making them a reusable overcurrent protection device. Next, we'll talk about fuses, which are one-time overcurrent protection devices that contain a fusible link that melts and breaks the circuit when the current exceeds a certain level. Fuses must be replaced after they blow. Then we'll discuss ground fault circuit interrupters, GFCIs, which are designed to protect people from electrical shock. GFCIs detect ground faults and interrupt the circuit to prevent injury. After that, there are arc fault circuit interrupters of size, which are designed to protect against fires caused by arcing faults. A size detects arcing faults and interrupt the circuit to prevent a fire from starting. And lastly, there are motor overload relays, which are designed to protect motors from overheating. Motor overload relays monitor the current flowing through the motor and trip the circuit if the current exceeds a certain level for a certain amount of time. We will now cover common wiring methods. Electrical wiring can be installed in a variety of ways depending on the application and the local electrical codes. Here are some common wiring methods. Firstly, conduit wiring. Conduit wiring involves running wires through metal or plastic conduit. Conduit provides physical protection for the wires and can be used in a variety of locations, including underground, exposed, and concealed locations. Secondly, cable wiring. Cable wiring involves running wires in a cable assembly. Cable assemblies typically consist of 2 or more insulated conductors enclosed in a sheath. Cable wiring is commonly used for residential and commercial wiring. Thirdly, surface wiring. Surface wiring involves running wires along the surface of a wall or ceiling. Surface wiring is typically used for temporary wiring or for adding new circuits to an existing building. Fourthly, underground wiring. Underground wiring involves burying wires underground. Underground wiring is typically used for service entrances and for supplying power to outdoor equipment. Fifthly, aerial wiring. Aerial wiring involves running wires overhead between poles or buildings. Aerial wiring is typically used for power distribution in rural areas. In addition to these common wiring methods, there are many other specialized wiring methods that are used for specific applications. We will now cover what branch circuits are. A branch circuit is the portion of an electrical wiring system that extends from the final overcurrent protection device to the outlets. Branch circuits are used to supply power to lighting, appliances, and other electrical equipment. There are several different types of branch circuits, each with its own voltage, current, and wiring requirements. Firstly, 120-volt branch circuits are the most common type of branch circuit in residential and commercial buildings. They are used to supply power to lighting, small appliances, and general-purpose outlets. Secondly, 240-volt branch circuits are used to supply power to large appliances such as electric ranges, clothes dryers, and air conditioners. Thirdly, multi-wire branch circuits share a common neutral conductor between 2 or more hot conductors. Multi-wire branch circuits can save on wiring costs and reduce voltage drop. Fourthly, individual branch circuits supply power to only one outlet or piece of equipment. Individual branch circuits are typically used for large appliances or for equipment that requires a dedicated circuit. Fifthly, appliance branch circuits supply power to one or more appliances. Appliance branch circuits must be sized to meet the requirements of the appliances that they serve. In addition to these common types of branch circuits, there are many other specialized branch circuits that are used for specific applications. We will now cover what a feeder is in electrical systems. A feeder is a set of conductors that extends from the service equipment to a subpanel or a branch circuit panel. Feeders are used to supply power to a larger area or a larger number of loads than a branch circuit. Feeders must be sized to meet the total load that they serve, including the demand factors and diversity factors. Demand factors account for the fact that not all of the loads on a feeder will be operating at the same time. Diversity factors account for the fact that the loads on a feeder will not all be operating at their full rated power. In addition to being sized to meet the load requirements, feeders must also be protected against overcurrent. Overcurrent protection can be provided by circuit breakers or fuses. Feeders must also be grounded to provide a safe path for fault current to flow back to the source. Grounding can be provided by a grounding electrode conductor connected to a grounding electrode. We will now cover what a service is in electrical systems. The service is the electrical supply from the utility company to a building or structure. The service includes the service entrance conductors, the metering equipment, and the service disconnect. The service entrance conductors are the wires that run from the utility company's transformer to the service disconnect. The metering equipment measures the amount of electricity that is used by the building or structure. The service disconnect is a switch or circuit breaker that can be used to disconnect the building or structure from the utility company's power supply. The service must be sized to meet the total load requirements of the building or structure. The load requirements are calculated using the procedures in the National Electrical Code. The service must also be protected against overcurrent. Overcurrent protection can be provided by a circuit breaker or a fuse. The service must also be grounded to provide a safe path for fault current to flow back